In science, we love to classify things. If we can find things that have a similar structure or a similar behavior, we like to give it a name. We like to label it. That way, if we find something in the future that has that same kind of structure or that same kind of behavior, we can attach that label to it and everybody knows what we're talking about. It turns out that in our universe, most things behave in one of two ways. They either behave like what we call vectors, or they behave like what we call scalars. Now, a scalar is anything that can be represented by a single quantity or a single number. So I have some examples in parentheses here, the number of pears in a sack. You can, if you have a sack of pears, you can count how many are in it. If you have 8 pears in your sack, that's a single number that tells you how many pears are in that sack. You could say the average temperature of the room. You could measure the average temperature of a room, and you could say it's 25 degrees Celsius or whatever it is, and that would be the average temperature of the room, something that you can characterize by a single number. Now, another example would be the distance from Memphis to Nashville along I-40. You could get in your car, you could drive from Memphis to Nashville, and then you could read on your odometer how many miles or how many kilometers you drove as you went. These are all examples of what we call scalar quantities because the answer can be represented by a single quantity. Now, there's another thing that is very commonly found in the universe. It's things that behave like what we call vectors. And a vector is a quantity that has both a magnitude and a direction. In other words, the amount is important, but the direction is important too. So, as an example, we'll consider force. Imagine you have a box that's sitting on the floor, and you want to push on that box with 10 pounds of force. Well, the motion of the box is going to be different if I push from that direction or if I push from that direction. That is, if I push it to the right, the box is going to move to the right. If I push it to the left, the box is going to move to the left. So the direction which I apply the force with, that matters. It's important. And so force is an example of something that we call a vector. It's something that has an amount. So you could say I'm pushing with 10 pounds or 20 pounds or however much the amount is. And then you also have a direction, to the left, to the right, up, down, whatever it is. But if the direction matters to what you're talking about, that thing is probably a vector. Now in this slide, we're going to be talking about what's called the equilibrium rule. And the equilibrium rule says that the vector sum of forces acting on a non-accelerating object or system of objects equals 0. In other words, we can write this as a mathematical equation. The sum of the forces equals 0. This funky symbol here, that's the capital Greek letter sigma, and that's a symbol that mathematicians use to mean sum, or simply add up. So what this says is that if the object is not accelerating, if you add up all the forces on that object, they have to equal 0. Now, another concept that we can talk about is the idea of a supporting force. The support force is a force that supports an object on a surface against gravity. So, in other words, we have this book here that's sitting on this table, and we have the force of gravity. The weight of the book is pulling it down into the table. Now, what keeps it from crashing through the table and falling on the floor is that the table has to exert an equal and opposite force upwards to balance the force that's pulling it down. This is that equilibrium condition. Because it's not accelerating, it's just sitting there. That means that the force that the table is pushing with has to equal the force of the weight. Now, this support force has a name that physicists often use, and they call it the normal force. Now, the reason for that is because the normal force or the support force always makes a right angle to the surface that the object is sitting on. And mathematicians use the word normal when they mean perpendicular or when they mean right angles. So it's just kind of a math terminology that physicists were familiar with and they started using. Now here's a fun conceptual test of this idea. So you have this guy here and he's standing on two bathroom scales. And the question is, when you stand on two bathroom scales with 1 foot on each scale and your weight evenly distributed, what will each scale read? Will it read your weight? Will it read half your weight? Will it read 0? Will it somehow read actually more than your weight? Well, that last one doesn't seem very likely. I mean, how could it read more than your weight? It's probably not going to read 0 if the weight is evenly distributed. And so you might guess, and if you did, you would guess correctly, that it's going to be half your weight. Half your weight is going to be the answer. So let's see why that is. We can say that if you are at rest on the scales, that means that the sum of the forces is equal to 0. The sum of the two upward forces is equal to the weight. So there's a normal force on the left scale, there's a normal force on the right scale. So those are the two forces pushing up. So the two forces pushing up have to equal the weight pulling you down. And so that means that each scale gets half of your weight. Now in the last lecture we talked a bit about friction and air resistance, so we can define it more properly here. Friction is defined as the resistive force that opposes the motion or attempted motion of an object through a fluid or past another object with which it is in contact. Wow, that's a mouthful. We're going to explain what that means in a second. But one other key thing that's very important is to note that friction always acts in a direction to oppose motion. It wants to oppose motion. It's always in the opposite direction. So let's imagine that we have an object that's sliding across the floor. Now, it's going to be sliding through the air, so there's going to be some air resistance, and there's also going to be some friction at the point of contact with the floor. So the point is that whichever way the object is moving, those friction forces, whether it be air resistance or fluid resistance, you could be swimming in a pool, you would have fluid resistance. Whatever kind of friction you have, whether it's air resistance or fluid resistance or the friction of sliding of one surface against another, the friction direction is always going to be opposite the direction of the motion. So if the thing is moving this way, the friction is going to be in the opposite direction. Now, what is it that creates friction? We can ask that question, and it turns out that there are two things that are very important. The first thing is what the surfaces are made out of, and specifically how rough they are. The rougher the surfaces are, the more friction you get between them when they're sliding together. And then the other thing that matters is how hard you press together. The harder you push two surfaces together, the more friction there is. Now, we have a model for that, and you can see I've got this green block resting on this blue block, and here they've taken a little bitty piece and they've blown it up. And what you can see is that even though these blocks might feel smooth to the touch, if you were to zoom in with a microscope, you would see that there's roughness. There are these little nooks and crannies. And so these nooks and crannies, they kind of get embedded in one another, and they basically prevent the thing from sliding smoothly. And that's the source of friction. And so the rougher the surface, the more deep those nooks and crannies will be, and so the more they'll kind of sink into each other. And also the same thing, the harder you press the surfaces together, the more you'll make those nooks and crannies sink into one another and lock together. So that is why friction behaves the way it does. Okay, let's look at this conceptual example. When Nellie pushes a crate across a factory floor at a constant speed, that means it's not accelerating. The speed is constant. That means it's not accelerating. The force of friction between the crate and the floor is A, less than Nellie's push, B, equal to Nellie's push, equal and opposite to Nellie's push, or more than Nellie's push. The answer is that the friction force has to be equal and opposite to the force of Nellie's push. Why is that? Because Constant speed means that the acceleration is 0, and that means those forces have to balance. How do I know that? Because that's our equilibrium condition. Remember, the equilibrium condition says that if there's no acceleration, the forces have to balance. So now we can look at another example. When Nellie pushes a crate across a factory floor at an increasing speed, that means she's pushing and it's going faster and faster and faster as she pushes. That tells you that the amount of friction between the crate and the floor is less, equal, equal and opposite, or more. What do you think? The answer is that the amount of friction has to actually be less than Nellie's push. Why is that? Because if it's increasing its speed, that means it's accelerating. And that tells you that you have to have an unbalanced force. If the forces were balanced, that would mean there's no acceleration. But if there's an unbalanced force, that means that it's going to be going faster and faster. So we can see in the explanation down below, this is reworded as the increasing speed indicates a net force greater than 0. It's not balanced. Her push is greater than the friction force. The crate is not in equilibrium. That's the key idea. Now in this slide, we're going to introduce two new concepts, the concept of distance and the concept of displacement. Now these are similar to each other and they're related, but they also have some very important differences. Displacement is the straight line distance between a starting position and a final position. Now it's important to note that the direction matters. So displacement is one of those things that we call the vector. Now distance is defined as the length of a path traveled. Now the length of a path is going to be something that can be represented by a single number, so that's going to be a scalar. Now let's look at the next slide and hopefully we'll be able to make these ideas more clear. Here I have an idea of someone starting at some point A and then moving to some point B. Now they could go one of two ways indicated in this picture. They could go straight across along the straight line path from A to B, or they could go along this more curved or meandering path. Now, the displacement is defined as the straight line distance from the starting point, which would be A, to the ending point, which would be B. So this blue arrow represents the displacement. And we could also measure the distance along that path. So if someone walks along the straight line path, they would walk some distance, which would be the length of that path or the length of that arrow, and they would also have a displacement from A to B, and it's going along this straight line path. Now the reason that we represent it with an arrow is because if you're going from B to A, you'd be going in the opposite direction, and that would be a different displacement. And so the direction you're going in matters for displacement. That's why displacement is a vector. Now, let's consider motion along this curved path. What would be the displacement? Well, it would be the same. It would be just this straight line path from there to there. But the distance on the curved path would be different. I hope you can all see that if you walk along the curved path, you're walking along a much longer distance than going along the straight path. And so the distance is the length of the path, and the displacement is a very special distance. It's the distance from the starting to the stopping point on a straight line path along with its direction. And having its direction is what makes it a vector. Now, this lets us continue because if you're going from some point to some point B, you're not going to do that instantaneously. You're not going to teleport. It's going to take you some amount of time to get from A to B. And so that lets us define two different concepts. We can define speed as the distance covered divided by the amount of time it takes to cover that distance. And so here we see a definition of speed is distance covered divided by travel time. Now we can also define a related quantity, which is velocity. And velocity, people don't know that velocity is actually different from speed, but velocity is defined as the displacement divided by the time. So that's a different idea. You have displacement divided by time, or you have distance divided by time. And remember, the displacement is going to be that straight line distance from the starting point to the stopping point. And since displacement is a vector, that means velocity is also a vector. In other words, when you're talking about a velocity, the direction matters. So you wouldn't say the velocity is 10 miles an hour. You'd have to say the velocity is 10 miles an hour to the north or to the east, or somehow you'd have to tell what the direction is. But if you're talking about speed, that's just the scalar part of it. That's just the number. So the speed would be 10 miles an hour, 20 miles an hour, 15 meters per second, whatever it is. Now, actually, what we're talking about in these equations are average speed and average velocity. And so we'll talk about that more in the next slide. So the average speed, for example, is the total distance traveled divided by the time of travel. That's different from the idea of an instantaneous speed. The instantaneous speed is the speed you have at any instant in time. So to give you an example of the difference of this, if you are pulled over for speeding, the police officer is not going to care that your average speed was less than the speed limit. You go from where you live to school. Well, if you pull out in front of a semi-truck to accelerate and speed past it, and you get caught by the cop for speeding, he's not going to care that you were going slower than the speed limit before. He's only going to care that at that moment in time you were breaking the speed limit. So it might be true that over the whole trip, your average speed was less than the speed limit, but at that particular time when the cop was looking, you were just very unlucky, and your instantaneous speed, the speed at that moment, was bigger. So here's a conceptual question to help drive this point home. So let's say the average speed of driving is 60 kilometers in 1 hour. That would be the same speed as driving 30 kilometers in a half hour, 30 kilometers in 2 hours, 60 kilometers in a half hour, or 60 kilometers in 2 hours. So if it's 30 for every hour, what do you think you would have in 2 hours? That's right, you would go 60 kilometers in 2 hours. So 60 kilometers would be what you would expect in 2 hours if your rate of speed is 30 kilometers per hour. Now, in the last lecture, we talked a little bit about the experiments that Galileo did with inclined planes, or ramps basically, where he rolled balls down these grooves that he cut into these ramps. And one of the things that he discovered was the idea that we now call acceleration. Now, today, the idea of acceleration is pretty obvious. You guys have all driven cars. Most likely, there's an accelerator pedal in your car that makes your car speed up, and a brake pedal that makes your car slow down and stop. But in Galileo's day, this was actually a new idea. People hadn't really thought about it. And what acceleration is, it's the rate at which velocity is changing. So if the velocity is changing, if the object is speeding up or if it's slowing down, then we would say it's accelerating. Now, because velocity is a vector quantity and the direction matters, we can also say that if something is turning, that also represents an acceleration. So here I've written down the 3 ways that an object can accelerate. It's accelerating if it's speeding up, it's accelerating if it's slowing down, and it's accelerating if it's turning or if it's changing the direction of its motion. All 3 of those, or any 3 of those, represent an acceleration of the object. And again, acceleration is the rate at which velocity is changing. Or you could say it's the change in velocity over the time that the velocity is changing. So this slide represents a summary of that. So acceleration is the rate at which velocity changes with time. So velocity is changing, and that change in velocity may be a magnitude. That means the amount of the speed is changing. Either it's increasing or decreasing, speeding up or slowing down, or it could be a change in direction, or it could be a change in both the speed and the direction at the same time. So acceleration is defined as a change in velocity over the change in time. So here's another slide to check your understanding of these concepts, and we have acceleration and velocity are actually essentially the same as each other, rates but for different quantities, the same when direction is not a factor, or the same for free fall situations. Well, this one's a little tricky. What do you think the answer is? So the answer is that they're actually both rates. Both acceleration and velocity are rates, but they're rates for different quantities. So what does that mean? Well, velocity is the rate at which position is changing. It's the displacement divided by the time, and displacement is the change from the initial position to the final position. So velocity is the rate at which position is changing. Acceleration, on the other hand, is the rate at which velocity is changing. When the only force acting on an object is gravity, that means you can ignore air resistance, you can ignore any other forces, only gravity is acting on the object. We say that that object is in a state of free fall. And it turns out that when an object is in free fall, it has a constant acceleration. The acceleration is a constant 9.8 meters per second every second. Now 9.8 is pretty close to 10, so you can, a lot of the time you can get away with just saying that the acceleration from gravity is about 10 meters per second every second. What that means is that when you drop a ball, every tick of the clock, every second, the velocity of that object increases by 10 meters per second. 10 meters per second every second. That's the acceleration. So we can write this out here. I've got 10 meters per second. That's the rate at which velocity is changing. So if something is in free fall, every second the velocity increases by 10 meters per second. Now, mathematically, we can rewrite this as meters over seconds times seconds, or meters per second squared. And that's usually the way we write the units for an acceleration. So we can write that as 10 meters over seconds to the squared power. So 10 meters per second squared. Now, what that means, though, is just a change of 10 meters per second every second. And what is this? This is the acceleration of a body that's in free fall. That is, only gravity is acting on it. Now, another thing that you can notice in this picture is the ball is falling increasing distances with every tick of the clock. So from, it's released from rest, and then in the first second it falls this far, and then in the second it falls that far, and the next second it falls that far. Each second it's falling a further and further distance. And that's always going to be true for objects in free fall, because what's happening is the velocity is speeding up. Every second the velocity is getting 10 meters per second faster, and so when it's here, it's going faster than when it was there. So it's going to naturally be traveling a greater distance over the next second. And it's, of course, speeding up as it goes. So it's getting further and further apart each interval. So we have this review question again to test our understanding. If a falling object gains 10 meters per second each second it falls, its acceleration is A, 10 meters per second, B, 10 meters per second, that is 10 meters per second, both of the above or neither of the above. Well, obviously it can't be both of the above because these aren't the same thing. It's probably not either of the above, and hopefully you remembered that the right answer is 10 meters per second. And we can write this as 10 meters per second squared. And unfortunately, the PowerPoint didn't write this right here. This should be a squared superscript here. The 2 should be up above a little bit. But anyway, you can fix that. So we can look at another example. A freely falling object has a speed of 30 meters per second at one instant. Exactly 1 second later, its speed will be the same, 35 meters per second, 40 meters per second, or 60 meters per second. What do you think it is? And hint, how much does it increase every second? So hopefully you got the right answer is 40 meters per second. So the starting speed is 30 meters per second. We know that every second it gains a speed of 10 meters per second. So 30 plus 10 is 40. So after 1 second later, its speed is going to be 40 meters per second because that's 10 bigger than 30. Now here's another review question. The distance that a freely falling body falls, does it remain constant with each second of the fall? Does it increase with each second of the fall? Or does it decrease with each second of the fall? I mean, does the distance that it falls get bigger and bigger with each second? Does it get smaller and smaller with each second? Does it stay the same with each second? Of course, the answer we've already said is that every second that the ball is falling, it increases its distance. The amount that it moves each second gets bigger and bigger. In fact, we can even write down a formula for the distance that a body falls. The formula for the distance that a falling body falls is that d, the distance, is equal to 1/2 a t squared, where a is the acceleration and t is the time. Now we know that for a falling body that a is about equal to 10 meters